Hey guys, so today we're going to discuss the Pythagorean theorem. The Pythagorean theorem is a very important theorem in mathematics. It's very fundamental and it's a good thing to know because you'll be using it a lot, especially, if you're also going into physics and such. It's a very, very important concept, uh, and it helps that you know it very well. And then honestly, it's not too hard to get a hang of. So let's get into it. What is the Pythagorean theorem? Well, the Pythagorean theorem gives us an important relation in Euclidean geometry between the three sides of a right triangle. It's an important theorem. So recall, what is a right triangle? Well, a right triangle, has a 90-degree angle in it. And let's call this side A, B, and let's call this C. Like I said, the right triangle has a 90-degree angle in it, and obviously we know that the longest side of a triangle is referred to as the hypotenuse. Now, in comparison to other types of triangles, so recall like an isosceles triangle, there's not a 90-degree angle in an isosceles triangle. But in the right triangle, we have a 90-degree angle. We have one 90-degree angle in, a right triangle. So let's continue. So let's see, what is the relationship? What is it? Well, the Pythagorean theorem says that, let's draw a triangle. A, B, C, and we got a 90-degree angle, and we got this is the hypotenuse, C is the hypotenuse. The Pythagorean theorem says that the side length A, in this case A, squared, plus the side length B squared is equal to the hypotenuse, which in this case is C squared. The length of the hypotenuse squared. Now, let's look at this a little more closely. Let's redraw this diagram. I'm going to draw this again. Actually, I'm going to draw this right here. I'm going to call the same sides, A, B, and C. And recall C is the hypotenuse. It's the longest side. Going back to this equation real quickly. Again, C squared is the hypotenuse. These are the shorter side lengths. So keep that in mind. We're going to discuss that a little more later, but keep that in mind. So let's look at this new diagram I drew. So we got a 90-degree angle, and let's pick on C squared. Let's pick on this term right here. Where have we seen a side length square? What does that mean? You got something side and you squared it. What does that give us? Well, if you look at this closely, think of a square in itself. A square with side lengths S. Well, what's the area of this square? It's just S squared. The area of a square is S squared. So if we think of it like that, we could think, if I drew a square here, around this hypotenuse, you could think, if one side, which is the hypotenuse, is length C, the rest must also be C, because it's a square, right? And if we do the same for A and B, well, if B is one side right here, then this must also have a length of B, so must this, and so does this. And the same for A, we get A, because one side length is A, and we're drawing a square. And a square has, the same side length all around. That's why it's a square. So, looking at this, going back to the equation, actually going back to the diagram, if you look at this, what's the area of this square? Well, it's just C squared. The area of this squared is what? B squared, because it's got side lengths B. And same for this one, it's A squared. So what is this saying? We can go back to the equation and we can look at this as saying the area of this square, A squared, the area of this squared, whose side lengths are A, plus the area of the square whose sides are B, is equal to the area of the square whose sides are C. So the area of this square plus the area of this square gives us the area of this whole square here. Interesting. But, maybe you're not fully convinced. And I'm going to do a visual representation of why this is true. Now, these two diagrams here, these two squares, are the same squares. They have the same area. So you're going to think that. They have the same area. Now, let's focus on the first diagram, so the one on the left. Okay, so we got these 4 right triangles with the same dimensions but different orientations. So, this A is the same as this A, same as this, and same as this. Same goes for the B's and the C's. And we got them, arranged in, different orientations. And by doing that, we formed this diamond. Now, it's not fully scaled, but imagine we got this diamond, so we just got this square shifted a little, shifted over, just rotated a bit, and to look like a diamond. And the area of this diamond, or you could think this rotated square, is, C squared. Because look, you got the hypotenuse of each triangle forming the sides of this diamond. So, what is the area of this? Well, it's just C squared, because, this diamond is just a rotated square. So the area of it is just still the area of a square. So it's C squared. Now, I've colored in a little with green here and blue the triangles, and I've labeled them 1, 2, 3, and 4. Pretend these are all colored in, like I said. And pretend the center region, this diamond shape in the middle, is not shaded at all. It's just white. It's left blank. Okay, now I want you to imagine in your head an animation. And this animation is going to take us from this first diagram to the second diagram. Now I want you to imagine this animation in your head. Okay, so let's start it. I'm going to use a different color. I'm going to use red. Imagine that, actually maybe I'll use blue. Imagine that you see this triangle 3. Imagine triangle 3 moved up until it collided with triangle 1. So this triangle right here, triangle 1. Triangle 3 moves at an angle and collides with triangle 1, and triangle 1 stays stationary. Okay, we do that. Now, imagine that triangle 2 moves down, and at the same time, triangle 4 moves right until they collide. And they're going to collide in this corner where triangle 3 used to be. Now, look at the second diagram. That's what we see. Triangle 3 moved up and collided with a stationary triangle 1. And triangle 2 moved down and collided with a moving triangle 4. Since triangle 2 was moving down and triangle 4 was moving right, and they collided right here. Now, basically all the colored sections, the colored triangles, they basically joined up. So we got a whole colored rectangle here with sides A and B, and we got another rectangle here with sides A and B again, right? This is B right here. This length is B. This length is A. Now, what happened to the non-shaded regions? This C squared in the first diagram, this non-shaded region, well, it got split into 2 parts. And look at it. I'm going to use a different color. Now I'm going to use green. It got B squared and B squared. The side of triangle 3 and triangle 2 here have become the sides of a square right here. And what's the area of this square? The area of this square is B squared. And looking at A, we got the side lengths A and A here. And obviously the boundary of the big square that's enclosing this whole thing. What's the area of this? This square right here, it's not drawn to scale, but it is a square. It's got two side lengths that are the same right here, right? So what's the area? The area is A squared, right? That's what we have here. So recall that all we did was reposition these triangles, rearrange them. We did not enlarge them or shrink them. We didn't change the area of the colored regions or the non-shaded regions. The white and colored regions, their proportions did not change. They're the same. I did not make any triangle bigger. I did not shrink any triangle. So therefore, by rearranging the colored triangles, just by moving them around, what I've discovered is that the area of the non-shaded regions, in this case it was C squared, is equal to then A squared plus B squared. Because what is the area of the non-shaded region? Let's ask that question. What is the area of the non-shaded region in diagram 1? Well, the area is C squared. Now, what's the area of the non-shaded region in diagram 2? Well, it's A squared, because A squared is non-shaded, and B squared. So A squared plus B squared. And since the non-shaded regions have the same area in both diagrams, that says A squared plus B squared is equal to C squared. Therefore, we've shown visually why the Pythagorean theorem holds true. Now, well, we've seen why it holds true. We've seen what it is. Now let's do some example questions. So our first question, and I'll cover more complicated examples in the tutorial, but just to introduce it, our first example is going to be quite easy. So we got some triangle, we got a 90-degree angle, and we got our side A, and we're going to say A is 1, has a length of 1. And we got our side B, and it's got a length of 3. And so let's write down our Pythagorean theorem, which is A squared plus B squared is equal to C squared. So one side squared plus the other side squared is equal to the hypotenuse squared, and we don't know the hypotenuse. So let's plug in our numbers. So what's A squared? A squared is 1 squared. What's B squared? Well, B squared is 3 squared is equal to C squared, and we don't know C squared. So if you add this up, this is 1 plus 9 is equal to C squared. So 10 is equal to C squared. So how do we solve for C? Well, we take the square root on both sides. So C is equal to plus or minus root 10. However, recall, we're looking for a length, so we must take the positive value. You're not going to have a negative length. You're going to have a positive length, right? So C is therefore equal to root 10. So when we take the square root, obviously we get two answers, but obviously we take the positive one because we are talking about a length. Okay, so let's do a little more complicated example. So we got some triangle. Draw it right here. Got our right angle. And we got our side Q. Now Q is equal to 4, and we got W, and W is equal to something we don't know actually. And we got M, and M is equal to 5. And we're solving for W. Okay, so now I wrote, and a lot of textbooks and a lot of places write the Pythagorean theorem always, A squared plus B squared equals C squared. These letters are just arbitrary. That means they're just randomly chosen. The letters are randomly chosen, but the relationship is what you need to understand, is that the two shorter lengths of the triangles, the sum of if you square each one and you sum them up, is equal to the square of the hypotenuse. You need to understand the relationship. So these letters are arbitrary. They're random. I could have any letters describing this relationship. So Okay, so let's do this question. So what's the hypotenuse? Well, identify the hypotenuse, and the hypotenuse is, well, represented by the letter m, and it's equal to 5. The length of the hypotenuse is 5. And so what is the side length? Well, q is a side, and w is a side, and we don't know w. So let's write down a relationship. So q squared plus w squared is equal to m squared, right? Because this is the hypotenuse, recall. So, well, let's plug our numbers in. So what do we know? Well, we know q. Q is 4, and we square that. We don't know w, so we just can keep that, w squared. And we know m is 5 squared. So, well, let's solve. We got w squared is equal to 5 squared minus 4 squared, and w squared is then 25 minus 16. W is then, what's 25 minus 16? It's 9. That's w squared. So take the square root on both sides. You got w is equal to plus or minus 3, but we need to take the positive value since we're looking for a length. Therefore, w is equal to 3. Okay, so we basically just did 2 examples where we showed how to use the Pythagorean theorem, and I'll do more in a tutorial video, more complicated, perhaps some word problems. So you can check that out. For now, well, we've done a visual representation, and we've shown why this Pythagorean theorem holds true. So thanks for watching.